Hey ChemStars, we're here to check your Chapter 9 homework, 9.2 mole to mole. If you're in Level 2, this is your page 3 and then page 4. If you're in Level 1, this will be your page 4 and 5. Okay, so let's start with problem number 1 right here. It says, how many moles of H2 are needed to convert 5 moles of oxygen into water? I'm going to go through and try and color code, that way you'll see what everything corresponds to and how the factor labeling cancels out. But the first thing you have to notice is that our recipe right here, our balanced chemical equation, it's not balanced. We need to make sure it's balanced first. So remember, this is like our recipe, and this is where we get the mole ratios from. This right here, this is where we get the coefficients from. Okay, so is it balanced? H2, H2, that's fine. O2, O, uh-oh. So let's put a 2 in front. That gives me O2. That gives me O2. So my oxygen's fine, but now I got to fix the hydrogen. There's 4, 2 in front. Now we're balanced. Now we can go ahead. So like our setup here, let's divide our reactants from our products. Before you make brownies, do you have any brownies? Nope. So before you make water, do you have water? Nope. We're going to create some positive product. We're going to use up something. And they say we have 5 moles of water. So we're completely converting 5 moles of oxygen. So this is going to be 5.0. That means before the reaction starts, we have 5.0 moles of oxygen. During the change, we have used up 5. And after the reaction, there'll be none left. The other thing we can say before we even start is that we're going to have exactly enough hydrogen. Okay, so look at this bare skeleton part of the problem. Do you understand how I got this? If not, go back to your video lecture and review this topic. Okay, so let's start solving for some of the unknowns here. Remember, our mole ratio is unknown over known, or we call it the want over the have. So all the coefficients are going to be based on this 5 number. So we're going to, oops, I want to undo that real quick. We're going to use up 5 times the ratio of the unknown to the known. So for every 2 hydrogen, there's 1 oxygen. This is my mole ratio, the unknown over the known I'm trying to solve for, times that coefficient out front. Okay, so 5 times 2 over 1, what's that? 10. That means during the change, I'm using up 10 moles of hydrogen and there's none left. So if I use up 10 and there's none left, that means you must have started with 10 moles of hydrogen. And how much water are we producing? We're going to be producing 5 times the ratio of the unknown water to the known oxygen. So look at your recipe up here. The ratio, water to oxygen, is 2 to 1. See how the reds cancel out? We'll be left with moles of water then. So 5 times 2 is 10, over 1 is 10. So we're making 10 moles of water. So how many moles of H2 are needed? So we answered more than we had to. This is right here what the question actually asked for. We needed 10 moles of hydrogen. Okay, let's go into problem number 2 on this page. Similar, but now instead of getting water, we're making hydrogen peroxide, H2O2. So first check, is this balanced? Yep, but let's put those 1s in so we know what our coefficients are. Let's do kind of our skeleton outline here. So how many determined amount of moles of H2 need to convert 5 moles of oxygen? Okay, so the same input as before. So I'm starting with exactly 5 moles. I'm using up exactly 5 moles, and there'll be nothing left. What else do I know? I'm going to be using up hydrogen during the reaction, and there should be none left over. I'm going to be creating some positive number of water molecules, but I'm starting with nothing, and there'll be some positive number left when I'm done. Okay, so let's fill in this chart. So how much hydrogen am I going to use up? I'm going to use up 5, that's the coefficient from the problem, times the mole ratio from the balanced equation. So my ratio of the unknown hydrogen, 1, to the known oxygen, 1, I'm using up 5 times 1 over 1. That means I'm using up 5 moles of hydrogen. So if I used up 5 and there's none left over, I must have started with 5 moles of hydrogen. And for fun, let's just fill in the rest of the chart. So I'm going to be creating 5 times the ratio of hydrogen peroxide, which is 1, to oxygen, which is 1. So 5 times 1 over 1, that's going to be 5 moles of hydrogen peroxide. Now let's see how this compares to our previous problem. It's almost the exact same setup, but why is it different? Because the balanced coefficients are different. So here we're making H2O2. See, the ratio is 1 to 1 to 1. So if we had 5, we get 5. But here the ratio is 2, 1, 2. So we actually get double. Okay, one more problem on this page. Calculate the number of moles of CO2 produced when 1.5 moles of hexane, C6H14, burn in air. Now, remember, our little trick here. When things burn in air, it's usually you're assuming it's O2 oxygen. So let's do our kind of skeleton outline here. This is my balanced equation. This is my recipe for my mole ratios. So label this here. This is your recipe. This is where you get your mole ratios from. And what do we know? 1.5 moles of hexane. So before the reaction, there's 1.5 moles of hexane. What else do we know? Okay, there's nothing about leftovers or anything like that. That means I'm going to use up exactly all 1.5 moles of hexane, and afterwards there'll be none left over. I know that I'm going to use up some number of oxygen, and at the end there should be none left over. And I know before I start the reaction, there's no carbon dioxide present, and there's no water vapor present. But I'm going to be creating some positive amount of those products. Okay, so let's fill out this chart. So how much oxygen are we going to use up? We're going to use up, oops, wrong color. We're going to use up 1.5 times the ratio of oxygen to hexane. Ratio of oxygen to hexane is 19 over 2. So let's use our calculator to make sure we don't mess this one up. 19 divided by 2 times 1.5 equals. That means I used up 14.25 moles of oxygen. So I used up 14.25 and there's none left. So how much did I start with? Well, that same number. Now let's try our carbon dioxide. So we're going to take 1.5 times the ratio of carbon dioxide to hexane. So carbon dioxide, the unknown, over the known hexane. So 1.5 times 12 over 2. Okay, 12 over 2 is 6. 6 times 1.5 is, use your math skills here, 9. 9.0. We've made 9.0 moles of CO2. Why did I go 9.0, not 9? Look at that, 2 sig figs. So technically over here, I should make this 14.3, but don't worry about rounding for sig figs in the middle of the problem. As we keep going, we'll actually do more steps, and we won't round for sig figs till the very, very end. And how much water vapor was produced? We're creating 1.5 times the ratio of water vapor to our hexane. So that's going to be 14 over 2. 14 over 2 is 7. 7 times 1.5, use your mental math skills, that's going to be 10.5 moles of CO2. If you want to be fancy right now and get the right number of sig figs, that'd be 11 moles of CO2. Great. Okay, so what we're going to do, we're going to flip to the next page and try and get this done before I run out of time on my video recorder. Okay, on this page, level 2 exactly matches what you have. Level 1 kids, same problems, but there's a little bit more structure here to help you out. So on these, I'm going to get them all set up for you, and then we'll stop and we'll come back and we'll check our answers. So let's go through the setup. So number 1, determine moles of silver chromate made from 0.4 moles of silver plus cations. So we got to do our before, change, after. Draw your line here dividing your reactants and your products. They're telling you there's 0.4 moles of this. We know that before we start, there's nothing here. We're creating some positive product. We're going to end up with nothing, end up with nothing. We're going to use up all 0.4. We're going to use up 0.4 times the ratio. We're going to create 0.4 times the ratio. Okay, that's the skeleton setup just from what's given in the problem. I want to go through and set these all up, and then we'll come back and check in case some of you don't have it done yet. Okay, next problem. BCA. Before, change, after. Separate the reactants and the products. How many moles of CO2 will be produced if 0.38 moles of ZNO is completely reacted? So we have 0.38. We're going to use up all 0.38. There'll be none left over. Also, for the carbon, we're going to assume that we're going to use up some number. There'll be none left over. And I'm going to be using up 0.38 times the mole ratio. Remember, you got to balance this to get the right mole ratios. Then over here, before I start, I have no zinc. I'm going to be creating 0.38 times our mole ratio. And over here, there's no CO2 before I start. I'm going to be creating 0.38 times the mole ratio. Okay, there's your skeleton setup for that one. Go through and balance, plug everything in, come back once I have these all set up. Okay, how many moles of hydrogen would be produced if 0.44 moles of CaH2 reacts with excess water? So this is a BCA problem. Before, change, after. Set up your lines, separate the reactants and the products. 0.44 moles of CaH2. So 0.44, it's going to be completely reacted. So that means I'm going to use up all 0.44. There'll be none left when I'm done. There also should be no extra water. Before I start, there are no products. You can't have brownies till you make brownies. And we're going to be creating some positive number of product there. We're going to be using up. And these are all going to be, the coefficient is 0.44 times the mole ratio. So plus 0.44 times the mole ratio and plus 0.44 times the mole ratio. Okay, there's your skeleton outline. If you haven't already done this, make sure you check that first, then go back and fill it in. Okay, two more. How many moles of nitrogen will be needed to produce 0.48 moles of ammonia? This one's a little bit different, but it's going to be the same process. Before, change, after. Do your setups here, separate that, separate reactants from products. Now this time, we just have to think about this a little bit first. They're giving us that we have made 0.48 moles of ammonia. So 0.48 is what was produced. We started with nothing. We don't know what the coefficient is here yet. So this part, I want you to think critically about how you could work backwards and figure out what goes over there. Okay, and let's set up our last one here. How many moles of oxygen gas are required to react completely with 0.0093 moles of hydrogen iodide, or hydroiodic acid? So B, C, A, before, change, after. Separate your reactants and products. 0.0093 moles of HI, 0.0093, completely react. Everything's all used up. So I'm going to use up 0.0093. There'll be none left over. How much oxygen are we starting with? We don't know. This is what we're trying to solve for, but we do know there'll be none left over because it's all used up. How much will be used up during the change? It'll be that coefficient, 0.0093, times the mole ratio once you've gone through and balanced this. Before I do the reaction, do I have any products? Nope, so these are starting at 0. We're going to be creating some positive product, starting at 0, creating some positive product, and then we're going to be creating 0.0093 times the mole ratio. We're going to be creating, for the same thing on iodine, 0.0093 times the mole ratio. Okay, so I've gone through and shown you all the skeleton setups. So if you have any mistakes in your work, go back and fix them. Pause the video, do the math, and come back and see, do you have the right final answers? Welcome back, ChemStars. Let's now check your works. Number 1, how many moles of the silver chromate will form? 0.20 moles. Look at your work right here. There's my mole ratio. Type it into your calculator, you get 0.20. Number 2, how many moles of CO2 will be made? Okay, so we're focusing on the CO2 column. Started with none. The coefficient is 0.38. Then the mole ratio of the unknown carbon dioxide to the known zinc oxide, 1/2. So 0.38 times 1/2. 0.19 moles of CO2 is produced. Check your other work too. Make sure those numbers came out okay. Number 3, how many moles of hydrogen will be produced if 0.44 moles of calcium hydride reacts with excess water, or with enough water? Okay, so look at this one, moles of hydrogen, started with none. I'm creating the coefficient, 0.44, times the ratio of the unknown hydrogen to the known calcium hydride. So 0.44 times 2/1, let's just double it, 0.88 moles of hydrogen. Okay, number 4, moles of this one was the one you had to think a little bit creatively for. So here's what you know. We created during the change 0.48 moles of ammonia. That means it's going to be question mark times the ratio of ammonia to the nitrogen. So nitrogen, that is actually our, I know we don't know it, but we're treating it like the known. We're getting it to cancel out. So we want to know how much of that there was. So question mark times the ratio will tell us what the question mark is. So follow my algebra over here. 0.48 is equal to 2/1 times question mark. I just took this over here. I isolated and solved by dividing by 2. That means question mark is 0.24. So I started with 0.24 moles of ammonia, or nitrogen, used it all up, there's none left. Let's see if that math works out. Here's our double check. If we plug in 0.24